Welcome to the class on reinforcement learning and artificial neural networks. In this video, I will discuss eligibility traces. Let's think of a mouse that searches for cheese in a one-dimensional corridor. So this mouse can walk around, and at some point it may find the cheese. So the corridor is continuous. All problems in the real world are continuous because our world is continuous. So what we can do is we can say, well, in order to apply reinforcement learning, to apply Sarsa, I have to discretize the state. And for example, we can say we have 10 discrete states. That would mean each state represents 20 centimeters if the corridor as a whole is 2 meters. But why 20 centimeters? We could also say, let's make it 10 centimeters. Then we would have 20 states for the same corridor. And now once we have these discrete states, we can then say, okay, I can go from a state somewhere in the middle, I can go downward towards the cheese and I get to this state, or I can go upwards in the other direction. Now let's analyze this just a little bit further. Suppose we play Sarsa and we initialize Q values at 0. And we always start trials at the top, which means here in this state S4. And then we update the Q values with Sarsa. And for the policy, we take the greedy policy, but in order to break ties, we take action A1. That means in the very first trial, since Q values are initialized at 0, we would basically walk down again, because each time we have a tie, we prefer action A1 and we reach the goal. Okay, and then we start again, and we start again in state S4. This is now trial number 2. And then I ask the following questions. After 2 trials, is it true that the Q value QS1A1 is larger than 0? QS1A1, where is this? This is down here. Okay? Is this larger than 0? Yes or no? Please think for a moment, stop the video, and the answer is yes, this is larger than 0. Why is that? Well, on the way down, each time you have to update the Q values. Now, once you have been in this state, S1, you went down in this direction. We said we take action A1 already in the first trial. And then in the first trial, we get the reward here. So we have a reward, and there's no further next state. So this Q of S prime A prime would be 0. We initialize at 0, but the reward makes that this is increased. So this is larger than 0. Okay, now let's ask the same question, but for QS3A1. This is up here. So question is, after 2 trials, the Q value QS3A1 is larger than 0. Is this true? Yes or no? Think for a minute, pause the video, and then I give the answer. And the answer is no. So what is the reason? Well, we said after the first trial, the Q value down here has been larger than 0. So this Q value down here is already positive. But as we moved around in the first trial, all the other Q values did not change. Look at an arbitrary transition. Look, for example, at this transition here. We had no reward, that was 0. The next Q value was 0. The existing Q value is 0 because we initialize Q values with 0. Therefore, it's 0 plus 0 minus 0, nothing changes. So in the first trial, the first Q value down here got updated. In the second trial, it's this Q value here which is interesting, because now we have if you look at the delta Q, we have a reward 0, but Q of S prime A prime would be Q of S1 A1, so it's already positive, so we get a positive change in the second trial. But in the second trial, we did not yet get a change of this one here. So basically, in the first trial, information goes up one step away from the goal, changes the Q value that leads towards the goal. In the second trial, it goes up to the second step away from the goal, and it would only be in the third trial that the information about the reward at the goal will arrive at the Q value, 3 steps away. That's all nice, but that's a problem. So the flow of information back from target is slow. The information flows 1 step per complete trial, per episode. But that means we need 20 trials to get the information 20 steps away from the target. But the world is continuous. The discretization that we took has been a completely arbitrary choice. And that means something is wrong, because it should not depend on our choice of discretization whether information arrives after 20 trials, after 50 trials, or 100 trials. How can we solve this? In this video, I will discuss a first solution, which is called eligibility traces. And this leads to algorithms that are called Sarsa of lambda, where lambda has something to do with the eligibility trace. Let's look here. It's not a one-dimensional graph. This is a two-dimensional graph. The target is this red square. And let's look at the approach to the target in the first trial. It looks like this. And then it would be on this final transition that we would get the update of the Q values. In the first episode, only the state next to the target will be updated. And now this is because we don't keep a memory of what happened earlier. And the idea of eligibility traces is to keep memory of previous state action pairs, and then this memory decays over time. So if we make the same trajectory, we would still have a decaying memory of this transition. In that state, we still remember we walked upward. So the way we do this is, if an action is taken in state S, then we update the eligibility trace by +1, and otherwise we just decay, and lambda is this decay factor. Lambda should be smaller than 1. Okay, and so this way we have kept a memory of the previous state action pairs, and now we update all Q values at all time steps with the standard TD error. We compare the reward with the difference of the two Q values, the temporal difference, and then we multiply with this eligibility trace. And now you can check for yourself. If you take lambda equals 0, then it's only the last state, the last transition, which is kept in memory, and then we are back to standard Sarsa. And here is the pseudocode of the book of Sutton and Bartow, here the 1998 edition. And I just want to point out that he writes an eligibility trace which is gamma times lambda. There is a deeper reason that will become clear later. In fact, the decay factor should not be lower than gamma. So if I multiply with gamma lambda, I can have the condition lambda should be smaller than 1. If I don't do this, the condition should be lambda smaller than gamma. So it's just two different ways to define this decay rate lambda. And here we arrive at this quiz. We go step by step. Eligibility traces keep information of past state action pairs. Is this correct? Yes, it is. For each Q value, Q of SA, The algorithm keeps one eligibility trace, E of SA. That means if we have 200 Q values, we need also 200 eligibility traces. And yes, this is also correct. So in some way, the eligibility traces are like shadow variables that run in the background. For each Q value, I have a shadow, and this shadow is updated all the time. Next question. Eligibility traces enable information to travel rapidly backwards into the graph. And yes, this is true. That was the reason to introduce these eligibility traces. The update Q of SA is proportional to this factor here, which is the TD error. And yes, this is also correct. And then final claim, in each time step, all Q values are updated.